Quaid here, and it's day 14 now of iste780, Data-Driven Knowledge Discovery, another lab day. And as I did with the last lab, I've already filled in the R commands here. I just have to execute them and talk about them. And let's see. I'm not going to do the why. I actually put in that width. I'm just going to take that out, actually. I'm just doing this so that my output emulates the book's output. So I thought I needed wide display, but I didn't. Okay, so we're going to do the chapter 7 stuff, the nonlinear stuff with the wage data. In fact, the whole thing is with the wage data. So the first thing that we're going to do is fit a polynomial model. And so we're using the poly function here to do a 4th degree polynomial of age as a predictor of wage. Now, keep in mind that coefficients of fit are not the only things that you can get. So these are all the things, things that you can access from the model. All right, but what we're interested in are the coefficients, and we can see that they're all pretty. They all look pretty good, except the 4th degree polynomial doesn't look so hot. So what's happened here is we've got the 1st, 2nd, 3rd, and 4th degree polynomial. So it's like, beta naught plus beta 1 times age plus beta 2 times age squared plus beta 3 times age cubed plus beta 4 times age to the 4th. And let's see, this is -2, so that's 1. So yeah, so to the 4th is the p-value is a little more than 5%. So that's a little beyond, a little bit worse than any cutoff that's prescribed. And I don't like to take p-values too seriously. There's a lot of backlash in the statistics world against the mindless use of p-values. And one of the things that people like to say, well, is a p-value of 0.0501 really that different from 0.050? And I think that you have to balance other factors. So the situation here is that we have a bunch of related, really good predictors, and a more parsimonious model if we just include the cubic. So personally, my opinion is that this model is a little has one too many predictors in it. Okay, now we can do the exact same thing, except that what we've just done with this polynomial regression is a linear combination of the predictors. So we can get the raw predictors by saying raw equals true, which is in this current line. So I'm fitting that model now, and I'm going to take a look at the coefficients. And the coefficients are different because these are the coefficients for the raw terms, rather than a linear combination of them. And I could do the same thing like this. So this next line explicitly calls out the raw terms, age plus age squared plus age to the 3rd plus age to the 4th, and we'll get exactly the same coefficients when we do this. Before we do this, I just want to mention that the I function here is a wrapper to protect the caret character from being used in another context. If we didn't have it inside a wrapper, it wouldn't mean to the power of. It would mean something else within an R linear model. So that I is just the I and parentheses around each term is just to protect it such that the term is interpreted as h squared, h cubed, and h to the fourth. So let's do that one and take a look at the coefficients of it, and you'll see that they're the same as the coefficients for the last one. Now, another way we can do this is to do cbind. So this binds the vectors together into a matrix, and it is also a wrapper function. So we can specify the h squared, h cubed, and h to the fourth in it. And if we look at the coefficients for this, they are, again, exactly the same. All right, so now let's plot this. So we want to plot the limits. We want the standard error bands. And now we're going to use this information to construct figure 7.1 from the book. The first command here is the par command. This simply establishes a matrix for the graphics to appear in, and the C12 means that it's going to be one row with two columns. So it'll be a panel of two plots that'll be possible. And unfortunately, it's going to appear off the screen here, so I'm going to have to move it onto the screen and play around with its size a little bit. I think I'll try to make it about this big. And so now I'll do the first plot. So this plot is just showing the raw data points. This plotting command is just showing the raw data points, age, wage. There are approximately 3,000 data points here. In fact, I think exactly 3,000 data points here. Okay, so I'm going to put a title on it, and where it says outer equals true there, that means that the title is going to go on the outer frame, and it's partially hidden here, but if we save this and put it into a, save this as a PNG or a PDF or something, and put it in, paste it into some other program, we'll be able to see everything that's hidden here at the top. Oh, you can't see it's going off the screen here anyway. So, but even if it were on the screen, as much of the title as you can see is all that you can see in my display. Actually, if you're using Windows or Linux, you may have a different display, so you may be able to see it. I don't know. Doesn't matter. What's significant here is that it is an outer title, so it spans both the panels. So we've started creating the first panel, and then we're going to do the second panel. Now this first panel we've created a plot for, but we can still do more commands to put stuff on this plot until we do a function that creates a new plot. So the plot command, for example, is the main function that creates a new plot. So these next few things here, like lines, so this is simply putting our polynomial regression line here, and this is going to put our standard error bands around it, and those don't create a new graphic. Okay, now we're going to do some calculations that are going to go eventually over here, but there are quite a few of them, so let me put this back on the display. If you look back at figure 7.1, it's got 2 or 3 items in it. Okay, so we're going to find out the maximum value of the predictors. Oh, okay, from fit 2. Okay, I see. So that was from fit 2. Now, what we would like to do is figure out which which of these models is better. And so we're going to do an Anova of nested models here. So we're going to have 5 models here, and we're going to compare them with an Anova. And we can do this anytime that the models are nested. And by nested, we simply mean that each model is a subset of the next model. So this first one just has age. This next one has age plus age squared, then age plus age squared plus age cubed, age plus age squared plus age cubed plus age to the 4th, and all of those plus age to the 5th. So each one of these is a subset of the next model. So the Anova is going to compare them. So we're going to create the models. Let's just do that really quickly. And then this Anova compares those models. And these are the models that we've created. Model 1, 2, 3, 4, and 5. And the way that the Anova works is that it compares each model to the previous model. That's why there's nothing out here for the first row. It compares each one to the previous one, and the null hypothesis is that there's no extra information in the one that's on the current line. So what's happened here is we should reject the null hypothesis because the F statistic is so gigantic, the p-value is so tiny. We should reject the null hypothesis that the second model doesn't add anything to the first model. And the same thing is true of the third model. We should reject the null hypothesis here. When we get to the quartic, we're in the same situation that I mentioned earlier, because our p-value is slightly greater than 0.05, and there are a lot of statistics textbooks that will tell you that you should fail to reject the null hypothesis if the p-value is greater than 0.01 or if the p-value is greater than 0.05. And in this case, it's slightly greater than 0.05, and it's a less parsimonious model, and the other models are great. So personally, the textbook, this textbook tells us that the cubic or the quartic are both good. The 5th degree is right out. We definitely don't want the 5th degree one. This is not on the borderline. This is on the borderline. I personally would reject it and say that the best model that we have here is the cubic model. Okay, and so here are the coefficients for that 5th degree model that I don't like. And when we look at them, we can see that several of them, this just tells us the same thing that we already know. These are the same p-values that we've just looked at. Okay, so now here's a different Anova. How is this different? This looks to me like it's just the first 3. Wage. Oh, and education. Education is here. Okay, so the question is, should we include education now? And we're going up to 3. So we've sort of said that the 3rd degree of age is good. So we're adding education to that now. And doing that Anova, we see that the first model performs extremely well. The second, the second model performs extremely well in comparison to the one with no polynomials, and this one performs pretty well. So a lot of people would fail to reject that hypothesis at the 0.03. So I would say that education definitely adds to the cubic polynomial. Okay, now another thing we can do is the logistic regression, predict whether wage is greater than 250K. That's actually what's in the other panel. So let's do that. That's what's in the other panel of figure 7.1. So we're just going to do the calculations for that. This is an alternative that is shown in the textbook but not used. Okay, so now I'm going to plot, and the plot command starts us going on the second panel here. And what's going to happen here is the plotting character, PCH is the plotting character, CEX is the character expansion, it's kind of a size variable. Plotting character is a bar, and we're going to jitter age on that bar. That means that we're going to slightly move the points so they don't exactly overlap each other. And you can see them over here. These bars become kind of like tufts on a rug. And now we're going to add the logistic regression line and the standard error bands. And you may recall this one that when we looked at this before, when we looked at figure 7.1, we saw that the standard error, this confidence interval, is really kind of absurd because there are so few people over the age of about 68 and so few people that earn 250 or more. There are like 70 people that earn 250 and a few dozen over the age of 70. So we don't have much material to predict with. Okay, and so here's what we've got in the age group. So you can see that most of the people. So this table tells us how this step function is going to work. We're going to create this step function, and you can see that in this interval there are only 72 observations. In this age interval there are this many. In this age interval there are this many observations. In 17-year-olds to 33-year-olds there are 750 observations. And this, again, I'm just doing this option to match the output of the textbook. And this is the step function that's used in this prediction. Okay, so the next thing to do is splines. So we're going to have to load the library splines. I believe that I already had the library splines. The only library I think I had to install today was GAM and its prerequisites. And so again, let me just mention, when you are installing something from using the R graphical interface, be sure that you check the install dependencies box. It's not checked by default for some unknown reason, and you need it. Okay, so splines. So let's load the Splines library. And the first thing that we're going to do are regression splines. And this is, all snickering aside, this stands for basis. And so these are basis functions. And when we do basis functions for age, we can either specify the knots or we can specify degrees of freedom. So first we'll specify the actual knots. I'll do this. Let's see. I think this is going to appear on the other side. So we've just created the plot here, and now I'm going to add the regression spline and the standard errors. First the top standard error, then the bottom standard error. So what we've done here is only one of several possibilities. We can see what the dimensions are of this, and then if we take a look at the dimensions of a basis of age, where we've posited the degrees of freedom instead of the explicit knots, we get the exact same result. And these are the knots. And so instead of having knots at 25, 40, and 60, we'll have knots at the ages 33, 42, and 51, and these are quantiles. So with 6 degrees of freedom, we're going to end up with 4 groups, and these groups are called quantiles, and in this particular case, they're quartiles. Excuse me. And so 25% of the observations will be in the group that has as its maximum 33.8, and so on. Now we can also do a natural spline. Instead of BS, we'll say NS for natural spline, and in this case, we'll set the degrees of freedom instead of setting the number of knots. And we can overlay that on this one. And this is sort of what you should suspect, that if we have fewer knots, we're going to have a smoother line, and the line is less flexible. And this lack of flexibility is evident right here. So you should expect that if you have fewer degrees of freedom, fewer knots, there's less flexibility as possible. And the converse, of course, is true. Okay, so now we'll plot the smoothing spline. That's figure 7.8. Did I miss anything here? I feel like I'm going too fast here, but obviously you can pause and just take a look at this. So here's a title without outer. So since we didn't say outer equals true, the default is for outer to be false, and for the plot title to appear just over a particular plot. There's not a lot of consistency in the way that the textbook is doing the plotting. I think it's just giving examples so that you understand what's possible with R, rather than trying to make every plot look a certain way. So now to do a smooth spline, so we've already done regression spline and natural spline. So smooth spline is a function called smooth spline. And we're going to say it has 16 degrees of freedom. So think to yourself, what does this mean for a second? What will 16 degrees of freedom mean? And what you should be thinking is that this is going to give a much more wiggly line. And this is going to have, so previously we had 6.8 degrees of freedom when we looked at this in the textbook. We sort of found that was a better model. Okay, so here is actually, this is a different one, right? Oh no, that was fit. Okay, so that's the one with 16 degrees of freedom. This one, we said do cross-validation, and so we allow it to automatically choose the degrees of freedom using cross-validation. And cross-validation found the 6.8. That's why we did this. Cross-validation came up with this number, which it did when we went over this in the textbook. And you can see that it's much smoother. 6.8 degrees of freedom is much smoother than the 16 degrees of freedom. So, and it's a dark art trying to figure out how many degrees of freedom, how flexible it should be, because typically you don't have enough data. You don't know for sure what the function is. But we definitely want it to be, if we believe that there is some function being obeyed, that if we believe that there is some underlying process, that there's some order to whatever process is producing the data, then we want enough smoothness that we have at least a chance of identifying that process. Okay, and so here's the command for the legend. So this is a relatively lengthy command, and it creates this very nice legend that the red line is 16 degrees of freedom and the blue line is 6.8 degrees of freedom. And we'll see legends like that in another plot coming up. Okay, now next is local regression. Wow, I'm really speeding through. I feel like I'm speeding through this perhaps a bit much, but of course you can always pause this and go over the individual commands, which I think are highly worthwhile. I think I mentioned that this is character expansion. I don't know if I mentioned this is line width. This is line type, and the line type can either be a number or a name. And over here we used the name line type equals dashed. And these are just known parameters to the legend command. The color parameter, the legend text parameter. C just is combining these. Top right is a location, and it isn't like we made this up. This is a keyword, even though it's in quotes, it's a keyword. Okay, now it's local regression time. So let's plot, what is this? Age by wage. XLim, age limbs. Okay, so we're back to this picture, and we put a title on it, local regression. And local regression is done by the LOIS command. And if you recall, we discussed the fact that the biggest decision that you have to make in local regression is the size of the span. A smaller span leads to a more flexible function. A larger span is less flexible. So we're going to emulate a picture from the textbook, which had two different ones. And so now we're going to put, so that's the first one with the span of 0.2, and this is the second one with the span of 0.5. And so, you know, clearly the span of 0.5 looks more reasonable. The span of 0.2 is overly flexible. And we can put a legend in here too. I'll have to switch the display so you can see it. So this tells us this key fact, because if you want to read these local regression lines, the key decision is what the span is. So you really want to know. It looks like parameters in like the lambda parameter. Okay, so now, moving on to generalized additive models. So here's generalized additive model number 1, and this one is using natural splines. And in order to do the GAM function, we're going to have to load the library GAM plus a bunch of other libraries. So I did a bunch I installed the dependencies, and it installed a couple of other things, including Akima, which we're going to use, or Akima, which we're going to use in a few minutes. Now, one thing I just wanted to do was look at the education variable. I think yesterday I said that I thought that the education variable had more levels than what we were seeing, but that's not the case. By simply looking at it, we see that it has 5 levels: less than high school grad, some college, and college grad, and advanced degree. Those are the five levels. Okay, so now let us do a, am I in here? Yeah. So we're going to create GAM model 3 first, before we create model 2. And now we're going to set up figure 712. So notice that here we've got, so this S function, what the heck does the S function do? I'm completely blanking on the S function now. Is that a spline function in GAM? I'm going to have to look it up. Excuse me a moment. I'm just going to pause this for a second while I look this up. Okay, and yeah, the S function is the smoothing spline in the GAM library. So whereas in the Spline library, smoothing spline was smoothing.spline, in the GAM library it's just S. So we've done a smoothing spline for year with 4 degrees of freedom, and a smoothing spline for age with 5 degrees of freedom. And now, oops, let me get back into this. I'm going to create a new frame. So now, up until now, these have been, I've been adding plots to these par frames. If I want to get, and the frames are a single row with 2 panels. Now, if I want to change that, in this case, I want to change that to 1 by 3, I can do that explicitly like this, or I could insert a command like this. Let me just do this just so you know. That closes off the previous. So anything that creates a completely new environment, a new graphics environment, as PAR does, will shut off the previous graphics environment. But I can also shut off the previous graphics environment by saying that. But right now I'm just going to do it the way the textbook does. So I'm going to say this, and that's just going to create this new graphics environment. And now I'm going to plot gam.m3, and the plotting command, the way the plotting command is going to work is it looks first at the object that I'm passing to it as an argument, and it's going to notice that that object, a GAM model, has its own internal plotting command. So it's simply going to step aside and let the GAM model use its own internal plotting command. And its own internal plotting command is going to give us 3 panels right away. And there they are. And these are the same 3 panels that are in figure 7.11. The only reason that they look different is the aspect ratio, because my display is, slightly screwed up here. If I were to expand this to fill my full screen, it would look like I could make it look like the textbook. And you should definitely, as you're doing these, you should definitely use your full screen. You should definitely resize these and see just see what it's like to create these. Okay, so that was gam.m3. Now I can explicitly use, so plot.gam is the plotting function inside gam. I can explicitly use that plotting function. Here the plotting function for R, it's that plotting function itself used this other plotting function implicitly because of the type of object that was. Now, if you think back to GAM1, is it up here? Yeah, it's right here. That's a linear model. It doesn't have its own plotting function. But if we want to plot it, if we want to use the variables in it to get the same kind of result that we got here, we certainly can. We have natural splines here, and education is a step variable, so we definitely have the material within the object to do this. So all we have to do is say plot.gam, and we'll get the same kind of plot, but using the linear model and the natural splines, which obviously does not look different from the smoothing splines, or at least in this case, it doesn't look significantly different from the smoothing splines. Okay, now we can approach this question: should we use year? So we've already looked at age and education, and we've liked them. Or at least I've liked them. I don't know if you've liked them, but the textbook liked them. R liked them. The evidence that we have shows that they add some value to the model. But what about year? So should we use it? And if so, how should we model it? Because GAM lets us model it any way we please. So let's first create a gam.m1 that does not have year in it. Then a gam.m2 that has year in it and has come on. Oh, year is a linear construct. So year here is just a linear construct, whereas it's a polynomial construct in gam.m3. Okay, and then we can do an Anova of these 3 models, because certainly gam.m3 contains everything that's in gam.m2 plus more, and gam.m2 contains everything that's in gam.m1 plus more. And this is saying f-test. This is not false. This is just saying the test should be the f-test. And here's the output of that. And the way that you read this is just like the previous Anovas. The first row refers to the first model. The second row is a test of the hypothesis that the second row doesn't add anything. And we would definitely reject that hypothesis. The second row definitely adds something. And so that's gam.m2. The third row definitely does not add something, or at least this is the probability of seeing this result or a larger result if the null hypothesis were true. So I would go with gam.m2 in the face of this output. So that tells me we should use a linear model for year. So let us plot gam.m2. Now, because we used the gam function, I can implicitly get the gam plot for m2. And very interesting thing about this is, if you recall yesterday, I said I didn't think this looked too great. And the reason that I didn't think it looked too great is because it doesn't account for the financial crisis of 2008. And what R is telling us is that that's just my own personal prejudice, and that the data is telling us that we should do this. So I think that's a very illuminating point. Our personal prejudices, are highly salient. Mine are, anyway. I mean, if you were around in 2008, you probably have some personal prejudices about it. Okay, and here's a summary of gam.m3. I don't know why the textbook chose this. I would have chosen a summary. Having done this, I would have chosen a summary of gam.m2. But in any event, the textbook shows this. Oh, I know why, because it's a perfectly legitimate model on its own. If we just looked at it, we wouldn't say that there was anything particularly... Oh, yeah, we would. I take it back. Yeah, we would say we would want to get rid of year to the fourth. We would definitely want to get rid of year to the fourth. That's what this row is in the output is telling us. All right, excellent. So both of these commands tell us that we would like that. Both of these commands, the Anova and the summary, both tell us that gam.m3 is inadequate. Okay, now we would like to make a prediction. And we're not going to do anything with that prediction. We're just going to move on to local regression. And this is going to plot the local regression. We said standard error is true. That caused the dashed lines to appear. Oh, I didn't mention the LO for local regression. So within GAM, so if we want to do local regression within GAM, we use the LO function, and we specify the span. So we've used local regression just for age here. Education is still a step function. Year is a smoothing spline with 4 degrees of freedom. Okay, now let's try a local regression with interaction terms. So if we do LO and we list multiple terms in here, they're going to be regarded as interaction terms. In other words, we're going to get year times age. And we can actually look at this if we use the Akima library. So if we plot this, we'll get a surface that, hopefully tells you more than it tells me. I don't really get much from this surface, and in fact, surface plots I find notoriously difficult to interpret unless I can rotate them. And I think we have explored some rotations in another lab, but we're not going to here. Okay, so here's another logistic regression GAM. And here's the plot. Oh, this is a plot. This is a plot that appears in the book. I did not make a note of this. I should have made a note of this. Yeah, this is a plot that appears in the book and that looks really outrageous over here. I'm going to pause again and figure out which plot number. Okay, so it's figure 713. I don't think I said that, so let me just add that to my notes, figure 7.13. And the issue is that this extremely wide variability, we talked about this yesterday, the extremely wide variability of the high school dropouts is because none of them, 0 of them, make over 250K. And the question here is, what's the probability that these guys make over 250K? So the presence of this has made all of these look the same. The presence of this is the variability in this is wiping out any information we could get here. So what we're going to do, and here we can look at this if we didn't know that there are no. So we only know this because I told you. If you didn't know this, you could just figure it out for yourself by doing this. So here's a table of education with the function wage greater than 250. And so you can see that that the assertion wage greater than 250 is true for 0 of the high school dropouts. And it is true for 5 of the high school grads, 7 of the some college, 22 of the college grads, and there are 45 people with advanced degrees who get over 250. And it's false. This is a very, very tiny number. Now, somehow this didn't look to me like it added up to 3,000. I was thinking that there were 3,000, and it didn't seem like it added up to 3,000, but in fact it does. So maybe it's obvious to you. It wasn't obvious to me, so I just did that. Okay, now let's do GAM without the high school dropouts, and that's pretty much the end. Yeah, that's it. We're going to do that and plot it, and that's the end of the lab. So let's see how we're going to do this. So this GAM is going to allow us to take a subset, and the subset is going to be education not equal to this. So if you recall, when we looked at the education variable, this was exactly what one of the levels looked like. 1 dot space less than sign space HS space grad. Okay, so so it's a string essentially, and what we're saying is education has to not be equal to that in order to be included in this model. So we'll run that model and then plot it, and we get the same effect that we get in figure, I think 714 in the book. Let me just mention that this is figure 714. Which is that we see the characteristic increase in probability of earning 250 with education. Okay, that's it for the lab. Thank you for your attention, and I look forward to speaking to you on day 15.